are, and where are we? We are looking at just Monte Carlo methods. Okay, so we motivated this from again at our particle jumping around, but now let's see how we can apply these ideas of Monte Carlo methods more generally. Okay, and so what is a Monte Carlo method? It's basically where you have just a probability of things happening, and you use that to create a bunch of simulations, and from that you can extract it. So it's interesting to know where this came from. Okay, so let's look at this from really the agent-based Monte Carlo methods. Okay, so where did this come from? It actually came from Los Alamos. Okay, and what they had was they had a bunch of really smart guys looking at radiation, and they're trying to see, you know, how thick does the shielding have to be so that it sufficiently protects people who are outside of some radioactive process. Okay, and they could write down the equations. They could look at the probability of something, you know, a photon having an interaction with something and then releasing energy and so on. They could write down all this. They could characterize all of it. But they have all this information and they couldn't put it together to actually find out how thick they needed to make their case. Cool. And so then they had the idea, well, what if we just do a whole bunch of random experiments? We know everything about the system. We can't solve it to get this value. So let's just actually simulate it, and then we can measure on average how deep, what the energy deposition is in this thing. We can calculate what a safe shielding thickness. Cool? Yeah? So what am I talking about? So this now is a huge area of research. Okay? Martin, you know anything about this? Yep. Okay, radiation safety. Okay, it's Monte Carlo methods. All right, looking at how much radiation are workers inside of nuclear plants exposed to. Monte Carlo simulations. Okay, of whatever species you have going through some material. Cool. Also, it's used in treatment planning for radiotherapy. So if you want to figure out how the energy is deposited in a tumor as a function of, you know, different beam strengths, different beam angles, you want to have like a treatment schedule, Monte Carlo simulation. Okay, so this is a gigantic area of research, and the basics for all of this research is really easy. It's what we've been doing so far. Okay, and so basically what we have is something where you can have something incident, okay, onto a sample. Okay, and this incident thing can be photons, electrons, protons, neutrons, some other kind of ion, heavy ion. Okay, but basically you have something that's releasing these things. Okay, something that's generating these things. So in radiotherapy, it could be, if it's photons, it could be some X-rays of certain frequency, certain energy. Okay. If you're in a nuclear plant, these might be neutrons. You're worried about neutrons interacting. Neutrons coming from your reaction and getting through everything, and then interacting with people and causing that to happen. Cool. And so you have a bunch of these, and they can either be from a single source. If you have some kind of beam, they might be in a tight beam. They might be coming from all over the place, in which case you can have them incident on your sample from a bunch of different directions. Okay. But this, again, you can just model based on what you're trying to see. Cool. And then what we can do is, experimentalists are really good at stuff. And so what we can do is we can say, okay, well, we have photons interacting with a certain type of material here. It could be water, it could be human tissue, it could be a metal. And so what's going to happen? Well, there's going to be interactions between whatever we have impinging on the material and the material itself. Cool? So there's a bunch of events. And those events will have interaction types. Okay? Because, as we'll see, different things can happen. And they'll have different interaction details. Okay? So in other words, what's produced? Okay? the trajectories of whatever is produced. The energies. The energies here, both of the products and the difference in the energy. Okay? So if you have something coming, a photon coming in with a certain energy, it has an interaction, and what it does is it ionizes an electron, and another photon comes out of there. So you add up the energy, the kinetic energy of the electron, and you add up the energy of the photon, you get a smaller energy than you had what going in. What do you think happened to the other energy?
Comes over thermalized or lost.
Exactly, it's deposited in the material. Cool. So an interaction can also lead to a deposition of energy in the material. Yeah? And this is actually what you want, like radiotherapy, right? Keep the stuff up, you want to damage the DNA inside the bad cells. Okay? So you want this energy deposit. Cool. These are things that we can just look up. We can have tables, the probability of certain types of energy. Certain types of interactions and the details of those interactions. What happens? Cool. Another super important thing about the interaction types, okay, is basically like the frequency of them, how probable. Okay? Because if we couple this with the speed at which whatever we're looking at is going through the sample, this can give us an interaction distance. Cool? Frequency coupled with the speed of whatever we have gives us an interaction distance. So really, this is a distance between interactions, between events. Okay? So again, we can measure all of these things. But if we measure all of these things, there isn't some magic formula we can plug it into, and that tells us, okay, if I have a bunch of photons in here, I get this energy deposition. So this is a good way to train those two. Okay, so we take all of that to construct event-driven Monte Carlo simulations. Okay, cool. You with me? So what's that actually going to look like? So let's do an example, and we'll do symmetry ionizing radiation. Okay, and so what we're going to do is take a number of incident photons, but let's just take one for now. Okay? So we have a photon coming in here. Okay? What kind of photon event types are there? You have ionizing. Photon, sufficient energy to ionize. Any ideas? Anyone remember this stuff? Did you study any of this besides Martin? What can happen? Yep.
Not sure.
Yeah. So there's a certain, so it's basically the photon can be scattered, right? There's different kinds of scattering. Anyone remember certain types of scattering? Compton scattering. You guys heard of Compton scattering? Yeah, what happens in Compton scattering?
I believe they just look at like the equivalent of this like hard interactions where you essentially have some distance before you're going to start just hitting stuff. And in that case, you start going in.
We can be a little more specific than that. What happens in compton scattering? We have photon interacting with some material. What happens? Hits an atom. It gets scattered. Ionizing. What do you expect that to look like afterwards? So we have a photon coming in, right? So what's it going to look like? Well, if it's scattered, the photon's going to take off at a different angle, and it's going to have a different energy, right? And I should actually draw it. If I do that like that, I should draw this with a longer wavelength and indicate that's lower energy. Cool? Well, that's terrible.
That's okay.
You just use a different.
I can do. I can do this. I can do this. Okay, like that. Cool. And what else happens? Compton scattering has enough energy to ionize. Yeah, an electron also takes it. Okay, so that could be a Compton scattering. Cool. Any other type of event? So Compton scattering, photons deflected, it loses energy, right? And the electron is ionized. And this is an inelastic scattering event, which means that energy is left behind. Okay? So if we wanted to calculate if we see energy deposition in material, we have some energy. Cool.
Is that from the electron or from the nucleus? Like, are we just assuming the electron doesn't make it very far?
No, the electron goes far. So there's energy lost in the scattering itself.
I mean, not in the electron particle.
That's right. Yeah. And then now as the electron moves through the media, it continually deposits energy. Right? Okay, because it's not a photon, it's chugging through this. Okay? So we'll talk about electron type events in a minute. But everybody cool with this? Because you can kind of see where we're going, right? Even if we just had this one thing, actually our life would be really easy, then we could calculate, you know, okay, let's shine X-rays on this tumor here, and we can calculate the energy deposited. So we just have to do a whole bunch of these, right? Millions, billions. Cool? Okay, but there's other types of interactions. Air production. Okay, so a photon near a nucleus spontaneously create an electron and positive pair. Okay, and there's actually recoil energy in the nucleus, which amounts to energy being deposited in our material. Cool. So that's just another type. Okay. So we're producing electrons. So now we have to worry about electron event types. So this is not an exhaustive list of photon and electron types. Okay. There's also like for Rayleigh scattering and stuff like that. Okay, I'm just giving you a couple of examples. You can build a model as sophisticated as you need for your business. Cool. How about electron type events?
You can just have absorption of electrons and one of that type, or
Yeah. Well, photoelectric is one. That's actually like a photon, right? Where you know, photon. Okay, so that's another one I did for a second.
I think this doesn't get much information.
I'm not going to worry about much or little or anything like that. I just want to paint a picture of how you do this. What do electrons do as they go through? Yeah, so there's kind of like a continual deposit of energy along the electron's path, right? It's interacting with all this stuff. Okay? So when we have an electron like this, it's kind of continually losing energy All right, and that energy will be deposited in the tissue. Okay. And there's a couple neat examples. One which is a sweet German word, so we'll do that for awesome.
Sarah.
Sarah. Anybody know what this is? Martin?
It's breaking radiation.
Yeah, what's breaking radiation?
You've got a really fast charged particle material that has to slow down the acceleration on that charged particle releasing this photon.
Exactly. Okay. So if an electron comes near a nucleus, let's say, and has an interaction with a photon, and that slows down and deflects, okay, accelerating charges produce radiation. Right? So what happens is the electron is deflected and slowed down. So I think this literally is breaking something. Breaking radiation, I think. Breaking something. And a photon is created.
Yeah, breaking radiation.
Cool. Another one that has a sweet name, delta rays.
Mm-hmm.
Cool. What are delta rays? They are just an electron ionizing. Okay. So you basically have an electron coming in, ionize it, has an interaction with an atom. It's going to ionize another electron, and so it's going to be cool. So there are more interaction types. And different interaction types matter more or less depending on what instant particles you have, what energy they have, et cetera, et cetera. Okay? These are just some examples. But let's look at what a possible track of a particle might be. Okay? And so let's say we have an incident electron here. Okay? We have an electron moving through time. And so we can have a probability of the electron having these different events. And here I only have two. Okay? But at each time we can do a probability check, right? So let's say, 10% of the time, so we have a certain time step and we know how long it takes for these interactions to happen on average. We can have a distribution of these types, right? And we can say, okay, well, when a random number is less than 0.1, so 10% of the time, we can have this kind of event, right? So as a function of discrete time, we can march through and just calculate, is this event going to happen? Cool. So let's say we get a Bremsstrahlung here, okay? So our electron is going to be deflected, and we're going to produce a high energy photon. Cool. Okay. So now in our simulation, we have to keep track of not only our original electron, but we've added a photon to the system. Okay, so an interesting thing with these simulations is that particles appear in disorder. Okay, it is cool. So then what happens here? Well, let's say the electron undergoes a bunch of delta ray radiation. Okay? And so it kicks off another electron here. And this electron is going to be lower energy than our incident electron. Okay? So it travels here and then basically dies. And when a particle dies, basically its energy is below some threshold. We don't care about its energy anymore. It's too low to have any significant effect on our system. Okay? So it kicks another electron here. This electron keeps depositing energy along this track here at some rate. And then it's below the threshold energy, we just get rid of it. Cool? So we had to add this electron. We can calculate its energy deposition here, and then it just cool? Yeah. And so I'm basing this off a picture in a famous review. Okay, and so I have a bunch of these interactions. Okay, and then that's it for that electron. Cool? All relevant energy has now been deposited in the system with these various mechanisms and at these various locations. Cool. Well, we have this photon. Let's not forget about our photon. Okay? What does our photon do? It has Compton. Takes out an electron, lower energy photon here. Now that photon can actually leave our sample. Okay? Which is another way it doesn't matter to us. Don't do that. I'm a little springy class. What's that?
I'll just talk of Compton and make it straight out of Compton.
There you go. So if someone chooses to do this for the project, which is an excellent idea, you can name it straight out of Compton. Okay, so this is kind of a neat simulation. So you can see how this is just a Monte Carlo probabilistic, right? We have a certain probability of events happening. When they do happen, they have certain characteristics. Because we can know the energy deposited, we can know the energy of the outgoing electron, we can have a distribution for what the angles will look like. We can just feed all of that into a simulation, let this happen a whole bunch of time, and then we can start to look at it as a function of time, where is energy deposited in this tube. Cool. And if it's really hot in one spot, we probably have a problem, we want the radiation spread out, so we can start developing treatment protocols that are based on Monte Carlo simulations. And this is how it's actually done, for better or worse. Okay? This is totally the basics of that, and it's an entire field of research, entire careers, entire departments that are dedicated. Yeah, it's a huge deal at UIT. Cool? So it's super simple, Monte Carlo. Okay? But it can be incredibly powerful. Cool? This is cool with people. Okay? I don't actually want to do a simulation of this, because I think it's a really good research project. Okay? I think you can already see how you might go about building something. I'm going to leave it for that. Okay? We've written enough programs similar. There's a couple of interesting wrinkles. Okay? Like you have to worry about creating and moving particles, but we can handle that. Cool? Yeah? Everybody okay? Okay, so this is an example, this is a really nice example of kind of an agent-based Monte Carlo simulation. You have nothing more than probabilities, and you're able to simply simulate a very complex system by basically just employing a random number. Cool? And we can actually do this for a lot of things. We'll come back to this idea of agent-based simulations a little bit more in the future, because we're going to come back and talk about rules-based simulations, which is going to have a lot of these ideas. Okay? But now we want to stay on Monte Carlo a little bit and talk about some different algorithms. So that's kind of like a pure agent-based Monte Carlo simulation, right? There's no real interaction or anything, right? So now let's consider two things that we have to have a little bit of a wire. Okay, and the first one we're going to talk about is metropolis Monte Carlo. Okay? We've already talked about this a bit. Because I did some foreshadowing last class when we were talking about sampling from a random distribution. So let's say we have some system. Okay? And what do we know about that system? We know the energy of the system as a function of the particle configurations. Cool? So we know some energy of the system. And so in the very simplest case, this could be like an energy. Okay? And what we want to do is start with a bunch of particles. They can have any initial configuration we want. And we want to evolve the system so that we get a representative, we get a bunch of states that represent the steady state solution, the equilibrium configuration. Cool? So how are we going to do that? Let's say we start with a bunch of particles at this location. Any ideas on what we can do to evolve this system towards the steady state solution?
This is an example where we're just letting it fall and roll around, like how we do something like this, or I'm trying to visualize how I'm trying to make this picture.
Sure, so they're not actually up here in space, right? They're down.
So what kind of particle?
Doesn't matter. Okay, these particles, the energy of these particles at different points, X looks like that.
Oh,
And we just want to figure out what the steady state solution is. What's the distribution?
Well, then you have the three molecular dynamic.
Yes, you can. Don't want to do
Using the droplet bucket parallel method that we just spent lots of time.
that. How can we use that numbers for random numbers?
If we identify the position of the particles with our random number generator. Actually, I have a question about that. Last class we looked at a random number generator, right? We said X was an evolved from this. So we never actually said how to use that to generate random numbers. So did we just sample?
No. So when you sample according to that, and so your X is walking around.
Yeah.
And just do a histogram of where you find the X.
Yeah. But in practice, how do you, because in practice, in the subsequent iterations of X are correlated.
Yes, they are.
So you have to wait like 1,000 iterations, or like how do you actually get a random number?
Right. So they're not random anymore. That's actually an issue.
So in practice, you would use it just sequentially.
We're actually using this.
All right, yeah. So position X is what was previously our random number.
So yeah. So what we can do, right, is we can take 1 or 2 or 3 particles, right? Take some part of our system and propose to move them to different locations. Cool. So we can say, okay, this guy I'm going to move over here, and this guy I'm going to move over here. All right. So, Martin, why are you smiling? Who are you talking to online? It's still not allowed. Okay, so we start, when they're all here, we start with an energy E naught. Cool. And then we propose to move some particles around. Yeah? And we calculate a new energy, 1. What do you think we do from here?
so you look at the difference of E1 and not, and if the difference is less, then we'll move particle towards E1. And if it's higher, then we're going to, with only a probability, move it to E1.
Awesome. Very well said. That's exactly what we do, which is exactly what we did at the end of last class. Cool. So that gives us a criteria, it's the metropolis criteria, to evaluate whether we should accept those changes or not. Cool. Everybody okay with that? Yeah? It's the exact same. And again, it's false.
So yeah, in this scenario, we're given the energy landscape, right?
Yes.
So why would we do
We
this?
need the energy line. We'll talk about that in a minute. Okay. So this is a very simple example, and we know how to solve this already. It's just raise flag. But we can use this idea in much more complicated systems. Okay? It's pretty cool here what the criteria is. Yeah? Okay. Icing model. You guys heard of it?
Magnets.
Icing model?
Oh, I think you said icing, and I was like,
Activity.
icing, yeah, we've heard of it.
Icing. You know?
Named after you.
Like a
Yeah, what is it? Icing.
It's studying the spin domains and ferromagnetic.
It's not just ferromagnetic.
Okay.
Anti-ferromagnetic. Anti to show how material can go from ferromagnetic to paramagnetic. I'm looking at. Cool. So what is it? Well, it's a pretty simple model. One de-icing chain. Okay, we have a bunch of domains. So these are going to be our discrete areas. Okay, so they're like agents, but we'll see that interactions are important. Okay, you can't treat each agent on their own. You can't treat the domains on their own. And these can have various configurations, basically spin up. Okay, then we have two ups, down, up, 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 down. You can write down, well, let's call the spins sigma, where sigma can be plus or minus 1. Okay? So each site has a sigma plus or minus 1. Cool? Plus 1 being up, minus 1 being down. Everybody cool with this so far? What do you think the Hamiltonian might look like? Remember, if it is time independent, then your Hamiltonian gives you your energy. What do you think should go into the energy? What do you know about magnets interacting? Yeah, exactly. So why do magnets behave a certain way? All the domains are, right? But they're all random. You don't have any net effect, right? Because everybody cancels out the domain. So there's obviously some contribution from looking at pairs.
Hold on, what's sigma? Is sigma
It's
the
just a
vector?
stick. It's just a stick.
The vector of all spin?
No. For each site. Right? So this would be +1, +1, -1. So sigma at this is 0. Sigma 0 equals 1.
So it's just the Hamiltonian for a single atom.
No, because we're summing over all pairs.
It'd be H of sigma.
Well, it's a function of these signal ij's. We can just write H. It doesn't matter. It's the energies. So I guess that should be H of the curly brackets. Okay. Right? Cool. Okay, so actually, we don't know that this is precisely equal to this. We could have some interaction. We do have some interaction coefficient, Jij, right? Well, no, just like what's the actual energy of these two interacting? It's not necessarily 1 or negative, right? And in fact, it could change depending on where we are in the picture. Okay, so this is the general. And it's actually customary to include a negative. Anybody have a guess why that negative is a nice thing to have? Yeah, because then if J is positive, which is nice, then when spins are aligned, you have a lower energy. Cool. In other words, positive J will give you ferromagnetic material, and a negative J will give you anti-ferromagnetic. Cool.
Is J also a function of their position?
Like how far they are apart?
Yeah.
We only look at neighbors. Okay. Okay. So this means we only look at neighbors, and we only look at each pair of neighbors once. Cool.
So J. So for the same pair of atoms at this point of the material, this point of the material, J is the same.
No, not necessarily. So J can depend on where we are in the material. That's why there's a subscript by J here. Is this cool with people? Is there anything else we should include here?
Sorry, in the sum, we're looking at adjacent pairs
Yes,
and every pair.
and every pair of bonds. Anything else we should include here? We can make it slightly more general.
What about an external field?
Yeah. Okay, what's an external field going to be? Well, this will not depend. We'll have some coefficient. Okay. This doesn't depend on the pairs. It only depends on the element. Okay. So we have a magnetic field in this direction, and it is aligned, and the spin is aligned with that. That would be a low energy configuration. So that's got to be our negative term. That's why we have a negative there. Just the magnetic field at each location.
Oh,
Right? It's not necessarily the same everywhere. Cool. Okay, so it's a really simple model.
does that view the permeability?
It's not the permeability. It's I gotta look at it. Yeah. But for now, let's just say the energy we get from this is going to be proportional to the magnetic field, and there's some proportionality.
What's magnetic permeability?
Well, it might be something like the magnetization or something. I got it.
I'm going to say you're
Cool. Everybody okay with this? So this is a 1D shape, okay? And this is the problem that you hopefully studied in some stat mech or material science course, okay? It's not too hard to solve. Let's try and do something a little bit more interesting, more difficult. 2D system, okay? So now we're going to have this exact same thing, except we add rows. Cool. Yeah. And let's add another row down here. And let's say we want to look at the energy contribution on this site here. What do you need to look at? What should we do? Previously, we just looked at nearest neighbors, right? What's our nearest neighbor situation? Right. Cool. This is our, sometimes hear this called as your stencil. Okay. What you're looking at is your neighbors. Cool. But numerically, it's no more difficult than this, right? Except now we loop over both rows and columns, but we just look at all our neighbors. Cool. Yeah? Everybody okay? So what do you think the system will look like? So let's turn off the forcer. What do you think the system is going to look like at low temperature? Not zero temperature, low temperature. At zero temperature, the system's quenching. What is at low temperature?
If you have an external magnetic field that's
No external magnetic field.
then
Yeah. So either up or down is going to win, depending on the initial conditions and your specific path, right? And what's going to happen is they're all going to line up along the line up or down, because that's the lowest energy configuration. And the thermal energy, the fluctuations are not big enough to do it at that state. Cool. So we'll probably end up with something like this. How about at high temperature? What do you think this is going to look like?
It's going to constantly bounce around because at higher temperatures, there'll be kind of thermal fluctuations coming in and out. They can be kicked from one direction. So it should be fairly random in terms of adapting.
So yeah, so what will it look like over time?
over time.
Well, okay, at any point in time, you look at your system, you expect it to look like
An equal number of ups and downs.
pretty good, equal number of ups and downs, right? So I'm going to go from ferromagnetic behavior to paramagnetic behavior, right? So remember, ferromagnets are magnets even if they're sitting on the low in the universe. Paramagnetic material can be magnetized, put in an external field, all the domains will align and will act as a magnet, but if you take away the external field, they'll all be random. Cool. And so we would expect the magnetization to be a function of the temperature. And in fact, we would expect a critical temperature. Which is given by that. Okay.
J.
J is that we're assuming J is just one factor. J is constant. That's J. Yeah, this is K on. So this famous result, dude named Onsager, heard of Onsager? It was this, showed up at a conference and just like wrote it down word of derivation. Kind of like Goodwill Hunting moment.
Oh,
Okay. And true story. And then someone came up with a very complicated derivation of it, and then sometime later, some time now after Onsager originally wrote it down, came with a very much clearer derivation. Okay. Yeah, maybe. It is some cool stuff, so we'll explain. What is this called when we go from a state of matter that looks like this to a different state of matter? Phase transition. Okay? So this is a simple phase transition. Cool. And so we know how to map this out. What can we do? Pick a J. Okay, T can be a variable that we can play with. What do we actually want to do in our simulation?
So we want to find the average number of like,
Well, we can calculate the energy of any state using this. Right?
Yeah.
It's just a formula we can chuck. Cool. So knowing the states of all our spins, we can calculate the energy of the system. Cool. So we start with some initial condition, calculate the energy. Then
So we randomly pick a perturbation, look at the adjacent state of the system, calculate the energy of that. If it's lower, then we switch to that. And if not, we switch to that. So
yes. Precisely. Cool. And we do this the smallest possible scale. We propose to split one spin at a time. We randomly choose a domain, and our proposition, our test state, would be to flip this spin at a time. Okay. Because if we try and shrink time down, you know, the single event that can happen is one spin. It's called single single spin flip. Okay, we can do one spin. Cool. Is cool with people? And then we can just actually look at what it looks like. But we can also do something. We can calculate some things about the system. Okay. So we can calculate the magnetization. This is pretty easy. Magnetization is just going to be the sum of the spins, right? Basically, how many of them are aligned? If it's random, what do you expect your magnetization to be? 0. And if they're all aligned in the positive direction, what do you expect your magnetization to be?
1.
1. Cool. We can also calculate the susceptibility. Okay, which is going to be the average of m squared minus average of n squared. Okay? Any idea what this gives? Well, this gives basically the fluctuations in the magnetization. Cool. And let's think about what that means for a minute. If you're at a low temperature, what do you think the fluctuations of magnetization are? Not very low, right? Because they're just always pointing in the same direction. If you're at a very high temperature, what do you think the fluctuations in magnetization are?
That's the standard condition.
But the fluctuations in magnetization. If you're at a high temperature, what do you expect the magnetization to be at any single point? 0. Yeah, so what are the fluctuations in them over time?
0.
Yeah, again, it's very low.
Yeah.
But when you're near the phase transition, yeah, you're going to have some domains spreading through the system where everything's positive, and you're going to have a large M value. Then there's going to be a big thermal fluctuation that's going to be overcome, and you're going to get a negative domain. You're going to get a large negative M value. And so your fluctuations in M are going to peak near the phase transition. Cool.
does I have a name?
It's the susceptibility. Okay. So here is our code to do that. So what I'm doing in the code now is I'm going to define a function here which basically calculates the change in the energy of the system when I propose to flip a certain site. Cool? And so what I'm going to do in my algorithm then is I have a nice two-dimensional array, S, which is going to be my spins. Cool. I initialize them to some random value here, either +1 or -1. Cool. And then I come down here, and I'm first going to equilibrate the system. Okay. So I'm going to let it try to reach some steady state. Cool. And so I'm going to do the Metropolis algorithm for a while, just letting the system basically, if I start a random configuration, I'm at a low temperature, it should condense into +1. Cool. So I'm going to try and let that process happen first. Where at a high temperature, it never reaches an equilibrium state, right? Okay. And how do I do that? Well, I find my position I want to look at, so I'm going to call that test X and test Y. That's just some position in my tube. Cool. And then what I'm going to do is, my proposal is to flip that spin. So I just multiply the spin at that location by -1. That flips it. Cool. And I calculate the energy before I do that flip, and I calculate the energy afterwards. With that function I have up there, that basically just does that sum the Hamilton. Cool. And then if test E is less than current E, I'm keeping just track of when I changed it, but I don't have to do anything else since I already flipped the spin. If that's not true, I have to do my probability check here. So I calculate my probability by the Boltzmann factor, pull a random number. If the random number is less than that probability, it passes the check. So I also don't change the spin because I already have. If it fails the check, I got to flip the spin back. Okay, it pulls over. Cool, and so I just multiply by -1. Okay, and that's it for the code. Okay, so if we're using probabilistic methods, we're just flipping these spins. We keep calculating the energy. We keep doing a random walk down to the low energy state. But we don't just sit there because we have thermal fluctuation, so we actually move around the energy state. A bit or a lot, depending on the temperature. Cool. Is this all right with everybody? So you can see how we built this out a little, random walk of particles, but this is actually much more abstract now. We're actually doing a random walk through phase space and looking at the energy profiles. Cool. So there's one tricky thing with Metropolis Monte Carlo. Maybe let's look at some movies first. So let me do this. Let me do it at a relatively low temperature. Okay, 1.5. Yeah. Okay, and I start with a random configuration like this.
Oh, that's cool.
Okay, let's see what happens over time. Well, we see our fighting domains here, right? But someone's gonna win. And money's on. Matt was here, I can.
Oh, that's that's really cool.
Okay, notice that here we have our periodic boundary conditions. Okay, so if you're on the edge, you actually look to the side.
Think you just do low boundary?
Yeah, you can do that too. You might get funny effects at the edges. If you do that, you end up with dynamics that are really dominated by what happens at the ends.
Why is it not rapid? That law has a very distinct square.
Yeah, I know.
Oh, there it is.
But it's kind of doing it there. But something might be wrong in the code. Most of it works.
If you rotate it, is it just like a two-dimensional surface?
Oh, I'm doing a little trick. I have 2 layers of particles here, and I just pop them up and down. See?
Oh, that's really cool.
Tricky. Cool. So low temperature, we end up in a ferromagnetic state. Cool. So let's see what happens if we increase the temperature. I'm going to go from 1.5 to 1.9. I think this is starting to get near the critical temperature, which is around 2.2 or something like that, 2.1. Let's see what this looks like.
In this case, with the higher temperature, the mains can still flip on the ground, right?
Yeah, so now we kind of have this. It's not so clear that it's going to condense to a single domain and stay that way forever, right?
So is this how the system actually physically evolves, or is this just a complication?
That's a very good question. Come to that in a minute. The answer, yes and no. Cool. So we're getting close to the phase transition, and things aren't so clear here, are they? You can have kind of red winning and then pink winning, right? But it's not so clear exactly what's going to happen at long times. Okay, and kind of do some time lapse here. That's true all the way to the end. Okay. Now let's bring it up just over the transition. So I'm at 2.5 now.
Yeah, that one we just watched is still the kind of same thing.
So now I'm just on the other side of the base where we expect the base transition. And you start to see that the domains aren't as big, right? You can get these small fluctuations. And when you start to get a domain, you get these smaller fluctuations. But we basically have a similar kind of picture to what was going on before. The size of the domains have changed, but we have the different parts that are fluctuating. It's not clear anyone's. Okay, but it's totally not completely random, right? We still have domains. Cool. All right, and that's true the whole way through. We can get big, like here, somewhere in here, we have an awful lot of pink, right? But it doesn't stay that way. Cool. And we end actually with quite a bit of red. So you can see your magnetization is going to have pretty big fluctuations. Okay. Again, we're near the phase transition. And if we go to really high temperature, what did I push the?
So in the case, it should just be flipping all over the place.
It should be pretty random. And thermal loads not too.
Oh, I think you need the character.
Yeah.
There's something before.
Oh, see. So yeah, this is predictable what this is going to look like. But it looks just more or less like a radon scenario. We're not at super high T, so we still probably can define some kind of domain size here, but it's starting to look pretty random. How slow is this code?
Yeah.
I don't know. So let's look at some of the results for a second, okay? So if everybody's cool with this picture, then so these are the results I have for the magnetization and for the susceptibility. Okay? And this is actually after pretty long simulations. You need awfully long simulations to get good averages and these readings.
I can imagine they're very
A lot. Okay? And similarly for the susceptibility. Well, we can see the main features here. We definitely go from magnetization of 1 to 0. It actually happens quite sharply. This is shifted off the critical temperature, and there's a couple reasons for that. One of which is the finite size of the system. Okay? But the critical temperature is also kind of the borderline of where you expect, above that you would have mostly zero magnetization. Okay? Cool. So that comes right out of solvers. Yeah. This is also a good environment to icing. Okay? And not just for 2D icing itself. There's a lot of stuff we haven't talked about with 2D icing. You can actually predict the magnetization of the function in temperature as well. It's actually kind of crazy. I'll write it down for this. There. Okay, that's not a function you see every day. All right. So there's a lot to explore in this. But actually, what I actually want to do instead of exploring that is look at a possible application. Okay? And in order to do this, we have to address Mark's question. Is that actually what the evolution of the system looks like in time, or is that just a way to compute it? Thoughts, opinions?
I think you can move in the low temperature because basically we're assuming that there's this single flip per unit time. The flips are not happening simultaneously. Right. But at high temperature, that doesn't seem like it's true.
Presumably, you can always shrink your time step low enough that that's true, right?
But you could also argue that for a sufficiently large system, many,
then you have to make it even smaller.
I guess.
Okay, so in that sense, yes, what we see somehow correlates to the evolution of the system. Somehow. But our answer is actually touched on the heart of it. What actually is that time step? Exactly how does that correspond to how this evolved and plugged in? Don't know. Okay? We know this is the probability of that spin flipping. We don't know how long that spin is. There is no explicit time step in Metropolis Monte Carlo, which means you cannot directly map it to the evolution of the system versus the time itself. You can map the evolution of states by, having the single flip dynamics. Okay, you can get an idea of how it's going to evolve, but it's hard to write down exactly what time it is at the end of the state. There's no time step in this anywhere. It's pure probabilistic.
In so there's like the Schrodinger equation, and I think there's a classical analog to that, where you can say like d of the state.
Classical analog to Schrodinger equation.
No, I don't mean in that sense. I mean where the state of the system depends on the Hamiltonian. The evolution in time depends on some function of the Hamiltonian. I think you can set out like a plus bracket.
That's not nonsense. That's good classical.
It is a classical mechanics, but so does that apply to a system like this?
No, because the thing is, remember way back when we talked about like escape from the well, or escape from the well is a good example. We started talking about, well, we expect the time to scale as the energy you get, right? We cannot say the time will be equal to it. There are more things that go into it. Cool.
So we can apply classical mechanics to the thermal system.
Well, you can. What you have to do is you have to start looking at like Kramer's escape processes and stuff like that, right? And if this spin flipping is really, going against the grain here, then it's an escape process. And what's the time associated with that? It's not just the exponential and the difference. Okay, it actually depends on the temperature rates. Okay, so there's a whole bunch of physics that we don't have in this problem, because we've actually just been concerned about what do the states look like, what are the ensemble of states in the thermodynamic. Okay, so how we get there will somehow give us an evolution of how things happen, but it doesn't give us an explicit time dependence because there's no time step. Cool. Is that all right with people? It's barely all right with me. This is something I need to study more to understand. Okay, but show an example. I don't think we'll have time for it today, where I want to compare 3 different Monte Carlo simulation methods and basically talk about, how they agree and disagree. And so we'll have to make some assumptions there to get Metropolis to agree with us. Two, basically we have to make assumptions. It means, everybody okay? Yeah? So, neat application of this. Oh, yeah, there's a couple cool applications. I'm just going to mention one. And if someone does 2D icing, they can also look at these applications and one motivate to not study the physics. but instead using these modeling techniques for whatever we want to look at. Okay? And there's a fun one. Opinion formation.
It's dramatic.
I don't know how to pronounce his name. Anyone does, open for suggestions. What's that? Yes, it is. Against all logic, it is. Okay? And this is basically a one-dimensional Ising chain. Hey guys, sorry, okay, and so what this says is, let's say we take a bunch of people, okay? And we can have 3 states for our people. They can be pro, con, or undecided. Okay? And let's say we take a scenario where we have pro people here. Okay? And on either side of them we have 2. Cool. So the one rule for okay, is called social validation. So if 2 people share the same opinion, then their neighbors will start to agree. Okay? So if we have this case, we'll end up with this case. Like we did at the end of the night at my barbecue. Right, Mark? All right. But if we have 2 neighbors that disagree, okay? Oh, sorry. Right as hell. Okay, and then we still have 2 undecided. Okay, this is called discord destroyed. Okay, and what happens is if these guys are arguing, this guy starts to argue with this guy. Cool, and this guy starts to argue with this guy. So what we end up with is like that. Cool. This is just like similar rules to the Ising. Okay, we only look at our neighbors. Depending on what our neighbors are doing, we can go ahead and construct these rules and let a simulation go. So you can see how Monte Carlo and rules-based simulations are so cool, and we'll talk about that more later. Okay, so you can actually run this simulation and you can actually get results about does everybody end up agreeing with each other or do you reach a state?
But stuff like that, like your final result is dependent on the initial state that you have, where you can kind of go through and figure out what your final state's going to be because it only depends on that neighbor. And so starting from the outside, you can kind of work your way in.
Well, that's why you can do things like periodic boundary conditions.
Oh, okay, so that's it.
Yeah.
Fair enough.
A system like this, it seems like you might want to.
You can do all sorts of crazy stuff. This is just, but this actually got a lot of attention. This guy got a lot of attention for this, and because he's really bridging statistical physics and like, social dynamics. Yeah. Okay. This is an application of how we can take a modeling thing, and we'll talk about another one that's going on in your lab room. Looking at Monte Carlo, model Twitter. Okay, that's another example where you take modeling process here, but you can apply it to something totally different and still get cool and interesting. Tell Isaac I said that.
And use this to win the election.
No. Okay, So let's talk about another application of 2D algebra. Okay? And what I want to do here is take my 0 field and turn it on. Okay? What are you guys doing? Passing notes back there? Yeah. Okay. Nucleation theory. Yarg.
Oh, the SZ, I think it's pronounced that stage. Nah.
Yeah.
That's even more, yeah.
Okay, so let's consider a system now where we have an external field, but we start all the spins opposed to the external field. Yeah? What do you think is going to happen here?
Is this an overall field or it's strictly overall?
No,
Okay,
overall.
yeah,
let's go.
okay.
Yeah. Any guesses?
So we have internal field pointing up and everything is pointing up.
Yeah.
So somebody's going to randomly point up and then it's going to propagate.
Is it?
Yeah, the temperature's high enough.
Because if one guy points up,
They all
he's with the external field. His neighbors want him down, right? Well, this is a metastable state.
So
You need a big enough random thing so that you get a big enough domain that goes against the field, and then that will spread.
So if it's a consistent external field, then basically it's going to be they're all going to be pointing down until we reach a point where the external field can flip everyone, and they're all going to just.
Well, not really. What it is this is a metastable state, right?
Yeah.
Because you're in an energy minimum here, but it's not the global minimum.
Yeah.
But to get out of it, you have to go higher energy, and then you can go to lower energy. Cool. Does this make sense with people? Yeah. So this is like when you have something like, let's say, a supersaturated solution of salt, right? Lowest energy state, you heat it up, you dissolve a whole bunch of salt, and then you lower the temperature. Lowest energy state is where it can form a crystal. But everybody is diffused the same distance from each other, right? Everybody's going to do this. They drop in a seed crystal. The whole thing. Okay? Similar with something like rain clouds. You have a whole bunch of water vapor. Not going to do anything about it until you have a speck of dust. And they collapse onto that, and you get a rain. Cool. This is nucleation. How does this process actually happen? Okay, and this is a nice model for that, right? Everyone kind of idea behind it. So our code is really the same. There's barely a point to show it. Except the only thing is that we now have an external field. Okay? So I'm setting my external field equal to 1 here. Cool?
So that just factors in that.
Yes, exactly. So I still have the exact same function up here. This is, I start off the energy to be the external field calculation at that site. It's negative S times the spin at that site, and then I go and loop over the neighbors. Cool. So I'm actually, to make more efficient code here, I'm not calculating the energy of the system every time. I'm just calculating the changes in energy of the system. That's ultimately all that matters. But again, it is not for a single domain. We have to look at the features. Cool. 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 Yeah. You can the energy based on a single domain, but there is interaction between that domain. Yeah. Okay. So, what does this look like? Well, let's do it first at a temperature of 0.5. See what it looks like. everybody's starting down here. And you'll see people flip up. They're going against the grain here. Very rarely. Okay, so at low enough temperature, okay, nothing happens. I'm going to get one guy to flip here. I'm only printing out every 10 because otherwise it's super slow. So you will have more spin flips there. But see, we saw an actual cluster flips, right? Once we got enough to flip, this thing now is just going to spread. Cool. So that cluster of like 3 of these flipping at once was the speed to totally change the state nucleation process. Cool. All right, let's look at it at a slightly higher temperature and see what it looks like. And so again, remember there's a subtlety here. This is, it's hard to map out the exact time, but it can give us an idea of the evolution of the system. So if a nucleation process takes longer for some combination of constants in the simulation, it's likely to take longer as well. In nature, it's just a question of what exactly is that time. That's harder to answer. Okay? So this is at a higher temperature. We can flip like crazy. Then we can actually get something rolling from every direction. We get very fast information. Cool. And so there's been a bunch of papers published using the 2D Ising model studying nucleation. Cool. Again, good project topic. Good. Yeah, stuff like how do they calculate the nucleation time?
So once they're all up with the field,
Yeah.
there seems to be a lot that are in flipping back in.
Yeah.
Shouldn't it be harder for them to flip down once everything is flipped out into the field?
Yeah, but we're at a high enough temperature, right, that those flips are still possible. They're just not going to propagate through the system because you're right? So you can think of it as being like, this is where we start. We have to climb in energy how we get there. This is where we end up. But we have some thermal energy, so we don't stay exactly here, but we only really sample these. Cool. So this is kind of like if we were to reduce this whole system to a one-dimensional system. We start here, right? We sample all these energies. We wait long enough to get this kick. We end up over here, and then we just fluctuate about this. Cool. Okay, so again, you can use very basic modeling concepts to actually get really fundamental insight to a wide variety of systems. They translate. Cool. Yeah. All right. Then that's it for today. We're almost done with Monte. What we're going to do is we're going to talk about kinetic Monte Carlo, which is a different algorithm. And the benefit of that is it explicitly has timescales. And then we're going to kind of compare having this agent-based MC, this metropolis MC, and the kinetic MC. See if we get the same results. Cool. All right. And I sent out an assignment on Tuesday. I already talked to you guys about that yesterday.